Okay, hello everyone. My name is Piotr and I came here all the way from Poland in Europe. I live in Krakow where I work at Virtus Lab and co-organize meetups. So if you are ever there, let me know. And it's fantastic to visit Japan and meet all of you. So I'm very grateful for the opportunity to be here and speak. So the functional programming gets quite a bit of recognition recently, for concurrency in particular. The ecosystem is maturing and getting quite much easier for newcomers to get into it. So I'm very excited about it. However, if someone is looking to learn it more in depth, which I think is very valuable knowledge, he will quickly find out that there are very little learning resources to do this. I hope that my talk could serve like a first step towards that. And it also means I will mostly focus on some things that I think are essential to have some kind of reasoning of what's going on. I won't do any overview of the library. I will just try to explain as I go. And I also won't fit why should you even consider functional programming. I assume that is sort of interested, but I just couldn't fit all of it. And lastly, I will use Monik's task for examples, but everything should apply regardless of what you use, even if you use futures. So starting from the very basic concepts, so let's define what concurrency is. And in my view, it's about doing multiple things interleaved. So even if we are able to only do one thing at a time, we can switch our focus to do many of them concurrently. And in my years of mastering the subject, I came to the conclusion that the best possible metaphor are siege weapons. So here we can use a catapult that is only one, and we can use it to attack two towers concurrently by just switching target. And we could say the catapult would be our CPU and the destruction of towers some kind of code that we need to execute there. And we'll look back later at this very animation and see some nuance in it which made me think that it is actually a good metaphor. So parallelism is not exactly the same, although related. And the way I look at it is that it is mainly about the efficiency. So basically, we want to throw more resources at some tasks to do them faster, either by splitting them or just doing some of them completely in parallel. So in this case, we wouldn't be able to use just one, for instance, CPU core or catapult. But for instance, we could use two to destroy one turret one faster than we would choose just one. And if it was slower, then there wouldn't be much point. So we need to somehow order the catapults or just utilize our CPU. And basically, and we call threads unit of CPU utilization. And what will matter the most in our context is that they can share memory, and then processor can run up to one thread per CPU core at the same time. So basically, this number will limit what kind of parallelism we can achieve. But even if we have just one, we can have a lot of concurrency going on. So thousands of towers. Specifically on the JVM, we have one-to-one correspondence. So when we call new threads in Scala, we also create an operating system thread. I'm saying that so you can have some intuition that there is also some cost to it. So it's not that free to create and also maintain. I think, but by default it's 1 megabyte of memory. So if we would have thousands of threads, it wouldn't scale very well in many systems. So here we will have two pictures that are very simplified and perhaps inaccurate, but should give you some high-level overview. So basically, each thread has its own portion of memory called stack, and this is where this 1 megabyte would go for. And it's like a private, and there's also a common space called heap, which threads can use to communicate. So basically, for instance, if we create some object in a thread, it will store like the reference as a local variable, and but the object itself will be on a heap. And usually, like the stack is quite small, and the heap is big. If we look a little bit like outside and look at the CPU, usually like each core would have some registers, some few layers of cache. Some of them also would be shared between CPU, and there would be a main memory. And here, like I think what's useful to know is that like what's happening on the JVM, so on our threads, and the data that we save can like end up in any of this place. So because like the closer the cache would be to CPU, it could also be faster, but also smaller. So ideally for performance, we load a lot of data in cache. But usually we have very few CPU cores, but we can have more threads. And since we can only execute one thread at the time on the CPU, sometimes we need to like switch places. So some other thread will want to start working, and when this happens, it is something that we call a context switch. So basically, there's some overhead related to it. So we don't have benefit from it that like a lot of useful data is saved in the caches, and that's why you might often hear that many times doing something synchronous, it can be faster than parallelizing operation. So even if you can do something in parallel, then benchmark it, because maybe this is so trivial that it's just faster to do it one at a time. And if we look back at the first example, we'll see that we can use one catapult to destroy 2 towers concurrently, but it will have to spend some time switching targets, so it pays some cost. It would be faster to just keep attacking one of them, destroy them, and go to the other. So fortunately, we don't have to manage lifecycle of our threads manually or create them or anything like that. We have thing from Java. It's called thread pools that does for us, and there are like several types that could reuse some threads, have limited thread pool, and so on. And basically, in the context of Scala, so like if you know execution context for future, then this is like a thread pool. Same with context shift for the case of KO, scheduler for Monix task. In Zio, I think this will be RTS. And basically, the thread pool could have some internal queue, and it would decide which tasks are executing on the threads it governs. But the operating system would decide which thread gets the time on the CPU at the given time. And here's a simple example of defining your own thread pool, in this case in Monix. So you will see that we basically wrap Java executor to create execution context, which we can wrap to have scheduler. So basically, it all depends on the stuff that is provided like long before us. But it's not just a simple wrapper. There are some extra capabilities that can be provided by these schedulers. And for instance, Monix is test scheduler, and other libraries have equivalents that can sort of manipulate time, which can be quite useful for stuff like testing some timeouts or forcing order of execution in tests, or even use different schedulers to see what's executing where. So in this example, I define task that rise error after 2 days. And for those of you that are not familiar with task or IO monads, So we could say that the task of int is like an description of a program that after running will produce either integer, will never return, or will end with an exception. And it's lazy, so until we run it, for instance like this, it won't do anything. It's like sort of build this description. And here we can like see how we can use such a scheduler. So we can use value on future to see if it's completed, and it's not because it needs to spend 2 days. We can, for instance, tick the 10 hours and it's still not there, or we can like 1,000 days and there we will have result. And of course we don't. Of course, this code won't run for 100 days. It will just happen right away. And there are like more things like specifying execution model, some tracing, and stuff like this. So in my talk, I want to focus on asynchronous boundary because I sort of think that it's like a fundamental thing that like if you understand it more or less what's going on, then you can have some idea how your code is gonna execute and debug a lot of problems. And it's basically about like our task just returning to thread pool, so scheduler, to be just scheduled again. So let's say if there are no other tasks, it will just go on the queue and get off the queue and execute again. And like many things can happen then. For instance, maybe you could figure out that it is supposed to be cancelled. Maybe another task would start executing in its place and the previous one would stay in the queue. Maybe it would just do this asynchronous boundary but still end up on the same thread it was before. New thread might be created or whatever we can think of. It will of course depend on the thread pool and what we do. And let's illustrate this. So here I defined a task that just it is infinite task that at every iteration we do this task shift. Task shift forces asynchronous boundary. There are various options for it. This one just shifts to the default scheduler, and the default is the one that is supplied when running the task. So you don't have to like pass it for operations. And we will just print on which thread we are currently. And in the output, we'll see that sometimes it just stays on the same thread, sometimes it changes, and it covers some of the scenarios that I pointed out in the previous slides. So let's see what happens if we don't have an asynchronous boundary. To do that, I create a scheduler with just single thread, so to make it simpler, and I specify synchronous execution model. I do this because by default in Monix there could be some asynchronous boundary inserted automatically in flat maps from time to time, and why I will tell later. So here is infinite task that just prints its ID. And we can do a tuple of them and call part tupled. This is from cats that will run them concurrently. And like we could expect that both of them run, but in reality, only the first one will ever like be running. And it's happening because we have only one thread, and until the task ends or does this asynchronous boundary, so we could think like contact this scheduler, it will just have this thread for itself. Like we could say that it's like blocking him. If we change it a little bit, just adding the shift every iteration like before, so this sign it will just we'll do this task shift and then repeat. And the rest is the same. And we will see at the output that it will just be 1, 2, 1, 2, 1, 2, 1, 2. And it's also, I think, it's easy to explain in your head because basically one thread, one task runs on this thread, the other waits in the queue. When the first task shifts, the second one was already waiting, so it got to this thread and it just kept happening in the loop. So we can see it's not like total magic. We can reason to some extent about it. So here I have more involved example to showcase maybe more when you have more thread pools and also more threads, then we have CPU cores. So the first scheduler will have 4. So this is the number that in theory I can run things in parallel. And then we have another scheduler with just 1. So we have 5 threads in total, and we could execute 4 in parallel. Again, this is an infinite task that doesn't do any asynchronous boundaries. And then I run 6 of those tasks in parallel, 5 of them on 4-threaded thread pool, and the 6 is running on the second scheduler. For instance, we can use execute on to do this. And if we look at the output, we'll see that every number except 5 is printed. So 5 of the 6 tasks are executing. And if we look at it, like it also might make sense to you already, because this 5 tasks we wanted to execute on the first scheduler, but there were only 4 places there. So only 4 of them were going, and they were going forever because of no asynchronous boundaries. And the 6 had thread for itself also in other scheduler. And the reason why the 5 could execute and not just 4 is because although as I mentioned, although the thread pool will decide which task will execute on the thread, then the operating system will actually schedule it on the CPU. Okay, so you might have also heard, or you might encounter, maybe reading some code bases, like in CatSFX library, Monix, and so on, something like light asynchronous boundary. I would consider it a bit more lower level thing. So I don't see it often in user code, but might be useful to know. And basically, it does the asynchronous boundary, but it just keeps going on the same thread. It's often used for stack safety because this could be a problem. I don't have it's out of scope of my presentation, but if you're interested, you can search the papers and check search for the stack safety in the code bases. For instance, in CatSFX, there you will see exactly that they deal with it using this light asynchronous boundaries, and perhaps could also then know that it is supposed to cancel. And I can illustrate it in example. So we can force this light asynchronous boundary like this, just using special execution context called, in this case, called immediate. And our task is also infinite. It just prints iteration and thread it is currently on, and then keeps going. Then we define a task that, first of all, we just print something when it is cancelled. And this start thing, it is not about starting execution of a task, but it means that it will return some fiber. You could think about a handle. The task itself will run in the background, and it will immediately go to this step in the for comprehension. And if we would like to join this fiber, or we can do it, or we can cancel it. And if we just cancel it, we'll see that it was going just on the same thread until it got this signal and just stopped executing. So And just as a bonus, this is implementation of such a scheduler. So it's like as simple as it can get, because like this, so it just synchronously run IBUs some like lower level thing, and if it's exception, just throws it. So no, and there aren't any like concurrency shenanigans there. Okay, so threads can be blocked, and we even saw it like with some infinite tasks. But usually when we like say about blocking threads, we mostly mean situation where it doesn't do any useful work. Perhaps it could wait for a response from synchronous HTTP client or wait for some I/O. And it's not good because it just wastes the thread, and as we mentioned, it can be quite expensive resource. And if we have limited thread pool, it could lead to some deadlocks, prevent other tasks from being scheduled, as we even saw in some examples. And the main practice is to just use dedicated thread pool for blocking operations, possibly unbounded, so that it depends. And for like our main like CPU bound task, to have number of threads close to the number of cores, so we can like maximize efficiency. And if you have to use something blocking, use timeouts, so at least it won't block and maybe hold to some resources indefinitely. And here's one of the way of doing this in Monix. We could have two schedulers, and let's say this is some kind of blocking operation. And this would be something that is CPU bound, so maybe it could do some useful calculations. And for instance, we could use this one for our like CPU operations as like a global scheduler, and I call here it implicit, so it's passed to the run, so it's the default one. But for the duration of blocking operation, I execute it on the blocking one. And it is shown in the output. So you could see like the thread pool names as the first thing. Okay, we have a concept of semantic or asynchronous blocking. So basically, there is sort of difference between blocking a task and blocking a thread, because you can block a task without blocking the underlying thread. So basically, it could wait for something like maybe a semaphore permit, and just like do it without taking the thread. So other things could execute in the meantime. So it's much safer, but you could still end up in the deadlocks if you have some wrong logic. So it is like much better, but it's not 100% safe. So here's an example. This one is a bit involved, so don't worry if you won't like understand it. I recommend like to checking it out from slides. But here I define a scheduler that has just one thread. And we will run 3 tasks concurrently that will do some blocking operations, and we will see if it can progress. So one task just sleeps for 50 milliseconds and then prints that it's done. And note that this is task sleep and not thread sleep, which blocks thread. And also sleep also like does as asynchronous boundary. So basically anything that is like semantically blocking will do asynchronous boundary. So first we can define semaphore. This one is from Katz effect. It's non-blocking. And one other task that we run is the one that waits 100 milliseconds, prints something, and releases the semaphore. We call start, so it will happen in the background. And then after the fact, we wait for the permit, so which is also like semantically blocking. And then we print done. and we run this and this other task in concurrently, and we'll see that despite having one thread, everything was able to progress. Okay. So now that you are a bit familiar with asynchronous boundary, I hope that you can understand the concept of fairness. And it's about different tasks being able to advance. So for instance, the situation when not all of them could ever get like the spot on the CPU is non-desired. And could lead to some consequences, like you could get some high disparity of latencies, like maybe some tasks might not execute at all. It's usually not pretty. And like to fight with it, so usually basically even if like the running everything synchronously can be more performant, it's good to introduce something from time to time. And for instance, the 1UC and 0 by default have strategies that introduces this from time to time, like let's say thousands of flat maps or so, which is configurable. And since Scala 2.13, also Scala future went this way, which is very good. Like because it used to like do asynchronous boundary and remap, flat map, and if you like write the code in more like a functional way, you will have a lot of it. And the overhead, not only you have these context switches, but also in asynchronous boundaries you allocate some extra objects. So like you don't want to do it too much. And usually you don't really have to think about doing these shifts. Many operations do asynchronous boundaries, like sleep or some races. The startup will also do it, and strategies like this also help. I will have a more like colorful animation to perhaps so the concept can stick in your head. So imagine your boss tasked you to defend the castle from the invaders, and you knew that they will prepare a lot of cavalry, so you're prioritizing the recruitment from the barracks. But suddenly it turns out that like something is throwing 90 kilogram projectiles, laying waste over your castles, and now you can only like look in terror at those superior siege engines. And it wouldn't happen if your stables could have some resources to recruit your own cavalry that could maybe raid the trebuchets. So, like to get back maybe to the real world, in case you don't do it for the living. So it's basically we could have this barracks could be some long-running synchronous computations that would take over most of your CPU, and like the tables, so other parts of your program will be just starved from the resources. Okay, I see that I have some time, so I will just briefly cover also the cancellation interruption. This is quite complex, so I like won't explain it very like in detail. And it's like sometimes we would like to just stop our computation, maybe because maybe it's not relevant anymore, and we want to save the resources. But we have to remember that not all of the tasks are cancelable. This cancellation logic needs to be somehow encoded in them. And also, like, often we don't really have a guarantee that the cancellation will happen at all, because if the task inside is doing some forever synchronous action or something like this, it will just keep going forever, no matter what we do, unless we just like turn off computer. And how we can make it cancelable? So there are many ways. For instance, asynchronous boundaries. So what I mentioned will like give this opportunity. So basically the cancellation is an asynchronous action, and like the lack of fairness, we also can't really expect our code to be cancelable. Some depending on the implementations, for instance, flat maps and even other operations could be this cancelable. Basically, you could think that internally there is some flag if the task should cancel or not, and it can be only checked in some specific places. It's possible also to add like support for interrupted exception in case you would want to cancel some Java I/O. But it's opt-in. Like currently, no, it's provided in Zio. I don't know of implementation for Kaio or Monix, but it's possible to do completely as a separate library, and it's not that difficult if someone needs it. Okay, and here I have some example of how to actually cancel a task. Earlier I shown like the start that could give some handle, but many operators have just this logic encoded in them. And in this case, so this function will just define some task that, depending on the number we give it, will just raise an error or sleep for 10 milliseconds and print when it started and when it ended. And we define 4 of those tasks, so 2 of them will fail and 2 of them we want to be cancelled in case other fails. And one of the way, like there is in one example called gather. So it's something like, if you're familiar with cas, it's like per sequence. So it basically takes a list of tasks, execute them all concurrently, and gets their results. So, and when we run it, we'll see that 4 tasks started. Then, so the string line returned this exception, the first exception that happened, and other tasks never ended because they could be cancelled during this time, and it was plenty of time to do it. And in case someone wouldn't want this behavior, that in case any of the tasks fails, the other are cancelled, I'd like to showcase a cool thing because like the task is referentially transparent. It's quite easy to compose different operators to get different behavior, even if they are not designed this way. So for instance, we can use a task wonder. So this is per traverse, just a bit more optimized. Basically, it works the way gather works, but also applies a function before executing. And in this case, we execute attempt, which handles all of the error in task and just return them as a value using either. So from the point of view of task, it's not failed because it has just an error as a value. So if no task is failed, then we don't cancel anything. And we can see this in the output. So now I'd like to showcase actually some dangerous thing with cancellation that I would like you to be careful for, and just to point out that there is no kill switch that you will cancel thing unless you really encode this logic by hand and don't even use the cancellation that is built in Monix, Zio, and whatever. So this is a happy case. It works. We just do some operations task that we would like to time cancel after if it isn't done in 150 milliseconds. So we print when it started, wait 100 milliseconds, print when it's between the sleeps, and in this sleep it will be timeouted. So everything works fine. But for instance, what if we have just one thread? And even more, what if this is not just a print, but some long-running or infinite synchronous code block? So again, we define the single-threaded scheduler, we have some task that represents synchronous infinite action. We use while true, but like in reality, it could be even some expensive algorithm that would run for hours, and you would just copy it from the textbook to make it as fast as possible. And it wouldn't have any asynchronous boundary, any cancellation logic, whatever. So just this, and we would want to run it between these sleeps. And we will see that the code, actually, if we were to run it, then it would never return, not even after this 150 milliseconds. This is because of two reasons. One is that the only thread that we have is taken by this while true, so there is nothing that we could execute the timeout. But even if we could, and we could send cancellation signal, then the task couldn't be cancelled, would be just running and keeping resources to itself. So you can't just cancel an arbitrary task. So keep that in mind. Okay. So one last thing that I'd like to talk about. So you might have heard about like green threads or fibers, and how does it relate? So very quickly, so usually I see that green threads are characterized by the fact that they are scheduled by virtual machine instead of operating system, and they can be like cheap to start. So it wasn't the case with our threads. But basically, we can have different numbers of this number of threads than we have operating system threads. And the fiber, so the slight white thread never really tells me anything, but I think it's mostly about the fact that it runs until it explicitly yields control to the scheduler. And we could ask ourselves, is task like a green thread or fiber? And if we look at it, like we can also like use quite cheaply use thousands of tasks and execute it on very few threads. Like asynchronous boundaries were like this cooperative yielding from fibers. Blocking like a task was like also wasn't blocking underlying threads, so was relatively okay. So there are a lot of similarities, and we often think about this, our IO monads like this. And like in case of something like Haskell that uses this model, we can learn from also from their books and experiences. And like even in fiber, there is a trait called fiber. So and for it, and even like in Zio, it is really embraced, and I think it's like a first-class thing that's everywhere in the code base. So that will be the end of my talk. I hope you like it. I have some links at Gitter channels that are really great. If you have some questions, also look for the documentation of this project to learn a lot about concurrency. And I will appreciate any feedback, not only about my talk, but also like the way we as a community explain these things. And thank you. Arigato gozaimasu.
Thank you for your explanation. You just mentioned canceling task and interruption. Can I increase or decrease timeout during the runtime? If yes, how can I do that? Thank you.
Okay, so you'd like a situation when you like specify a timeout, run the task with this timeout, and then would like to change it?
Exactly, yeah.
So I'm not sure about timeout operator, but I think you could like quite easily like write a combinator for it. I didn't cover it, but there is a concurrent structure like called deferred. So it's like a purely functional equivalent of promise. So your task could race with this promise. So the task race like runs two tasks concurrently, and the first of it is finished, then it cancels the other one. So we could race it with this deferred, And in other place of your program, you could complete the deferred, so basically signal timeout in this place. And if other place, you would like in other place to just signalize that it should happen, like for instance after 1 day, then you would just create a task that first sleeps for 1 day and then completes this deferred. So if you're interested, after the talk, I can show you example in code.
Okay, makes sense. Thank you.
Okay.